Researchers have found evidence of a cataclysmic energy flare that began near the supermassive black hole in the center of our galaxy. This catastrophic flare punched through both poles of the Milky Way far into deep space, creating two enormous ionization cones. The discovery can lead to a complete reinterpretation of our galaxy's evolution. The flare, officially known as a Seyfert flare, was so powerful that its impact was felt 200,000 light-years away, smashing into the Magellanic Stream, a long trail of gas extending from the nearby large and small Magellanic Clouds, dwarf galaxies orbiting our Milky Way. A team of researchers from Australia and the United States says the explosion was too huge to have been triggered by anything other than the nuclear activity associated with the supermassive black hole, the Sagittarius A, which is about 4.2 million times more massive than the Sun. Using data gathered by the Hubble Space Telescope, the researchers calculated that the massive explosion took place little more than 3 million years ago. During that time on Earth, the asteroid that triggered the extinction of the dinosaurs was already 63 million years in the past, and humanity's ancient ancestors, the Australopithecines, were roaming in Africa. The researchers estimate the blast lasted for about 300,000 years. Using a new method for hunting nearby black holes, astronomers spotted a huge stellar black hole in our galaxy, bigger than ever thought possible. This method will help us find many more black holes in the near future. Stellar black holes come from the death of stars, and despite billions of stars that exist in the Milky Way, we have only discovered a handful of these black holes. Until now, scientists had estimated the mass of an individual stellar black hole in our galaxy at no more than 20 times that of the Sun, but the latest discovery changes everything. The newfound stellar mass black hole is 70 times the mass of the Sun. It lies 15,000 light-years from Earth, and researchers call it LB1. The Milky Way galaxy may contain about 100 million stellar black holes. Until recently, stellar black holes could only be spotted when they were seen eating up gas from a nearby star. This process creates powerful X-ray emissions detectable from Earth that reveal the presence of the collapsed object. The problem here is that most of the stellar black holes in our galaxy aren't eating stars. Therefore, we cannot detect them this way. But that's when Professor Jifeng Liu of the National Astronomical Observatory of China, together with collaborators, observed the sky with China's Large Sky Area Multi-Object Fiber Spectroscopic Telescope, looking for stars that appeared to be getting pulled towards the gravity of an invisible object. After using that technique, follow-up observations using the powerful Gran Telescopio Canarias in Spain and the Keck Observatory in the US revealed a star 8 times heavier than our own Sun, orbiting the massive black hole every 79 days. Now scientists will have to re-examine their models of how stellar mass black holes form. A team of astronomers spotted a runaway star called S5 HVS1 traveling through the Milky Way at roughly 3.7 million miles per hour. The gravitational forces of Sagittarius A supermassive black hole caused the star to travel at such high speeds. The star lies in the constellation of Grus and travels 10 times faster than most stars in our galaxy. The high-velocity star will inevitably leave the Milky Way and never return. What makes S5 HVS1 so interesting is its high speed and close passage to the Earth, only 29,000 light-years away, which is practically next door by astronomical standards. We never knew about these ultra-fast stars until about 2 decades ago. They travel at sufficient speeds to escape the galaxy by overcoming its strong gravitational pull. It takes an incredibly massive object like the 4 million solar masses Sagittarius A to accelerate these stars at such velocities. Scientists think the black hole ejected the star with a speed of thousands of kilometers per second about 5 million years ago, a time when our ancestors were just learning to walk on 2 feet. Originally, S5 HVS1 was part of a binary system that got too close to Sagittarius A. Therefore, the supermassive black hole swallowed one of the stars and ejected the other at high velocities. This process is called the Hill's mechanism. The runaway star was discovered using the 3.9-meter Anglo-Australian telescope. With the help of the European Space Agency's Gaia satellite, the researchers also discovered the full speed of the star and traced its journey right back to the center of the Milky Way. For decades, scientists have theorized that there is a 9th planet orbiting our Sun. Based on their suggestions, the planet could be 10 times bigger than Earth and 20 times farther out from the Sun than Neptune. The scientists who predicted the planet's existence did so based on the strange, highly elliptical orbits of around 30 so-called trans-Neptunian objects. Another weird feature is that the Kuiper Belt, a circumstellar disk full of icy asteroids, comets, and dwarf planets which encompasses the solar system, orbits in the opposite direction to the planets within it. But recently, researchers published a paper on Archey titled "What if Planet 9 is a primordial black hole?" It suggests that the 9th planet is actually an ancient primordial black hole about the size of a tennis ball. Primordial black holes have formed soon after the Big Bang, 13.8 billion years ago. Astronomers believe primordial black holes with the lowest mass have probably evaporated. However, the larger ones may still exist even though we have never directly observed them. Because primordial black holes formed so early on in the existence of the universe, they are much smaller than their modern counterparts. However, now it could be a very difficult task for scientists to confirm this theory. With a mass of around 5 Earths and a radius of about 5 centimeters, the hypothetical primordial black hole would have a Hawking temperature of approximately 0.004 Kelvin, making it colder than the cosmic microwave background. Thus, the power radiated by a typical primordial black hole alone is very small, which makes it pretty hard to detect. If the hypothetical Planet 9 did turn out to be a black hole, it would also explain why it has been so far impossible to detect, as researchers have so far been looking for an object in visible light. But the researchers now propose examining cosmic rays and gamma rays, which could be emanating from the small black hole. Supermassive black holes can have major impacts on the evolution of a galaxy, especially when they are causing powerful winds to blow. When a black hole consumes the material of its galaxy, it means the galaxy has an active galactic nucleus. During this phase, the black hole is growing in mass and gas is being driven out by the energy released by the active nucleus. For this research, astronomers used the AMIR infrared spectrograph on the Grand Telescopio Canarias to study the winds of ionized and molecular gas coming from a quasar. The researchers found that ionized wind is faster than the molecular wind, reaching velocities of up to 1200 kilometers a second. But the molecular wind is emptying the gas reservoirs of the galaxy up to 176 solar masses per year, and it seems like it is preventing the formation of new stars. However, now astronomers want to observe a complete sample of obscured nearby quasars to study their ionized and molecular winds. This will allow scientists to directly confirm this effect on the evolution of galaxies.
First of all, we don't know exactly when the first black holes formed, but there are theories. In the present-day universe, black holes are formed when massive stars run out of fuel and collapse in on themselves. So a theory is that perhaps there were no black holes until the first giant stars collapsed, igniting a cataclysmic supernova explosion and leaving behind a black hole, perhaps 400 million years after the Big Bang. According to this model, the first black holes acted as nuclei for the creation of galaxies, drawing in raw star-forming material from the universe around them and growing in size to become the supermassive black holes with a mass of millions of suns that lie at the core of many of today's galaxies. In 2011, NASA's Chandra X-ray Observatory confirmed the presence of growing black holes in the heart of many distant ancient galaxies, which strengthens this theory. But another theory is that the first black holes were born in the first second after the Big Bang, some 13.8 billion years ago. Supporters of this idea suggest that in the first moments of creation, pressures and temperatures were so great that slight fluctuations in the density of matter could create black holes spontaneously, which could then have acted as the seeds for later star and galaxy formation.
Black holes are extremely hard to detect simply because they do not reflect light. The gravitational whirlwind of these black beasts pulls inward with so much force that even light can't escape their grasps. Even though we cannot see a black hole directly, we can detect the surrounding matter funneled by its gravity into a disk around it. As matter falls in, it settles in a disk around the black hole that can get very hot. Some of the energy released from falling in is turned into light, which we can then see in X-rays, which can be detected by X-ray telescopes such as the orbiting Chandra X-ray Observatory. Another technique used for detecting black holes is looking at how objects near one behave. For example, at the center of the Milky Way, we can see an empty spot where all of the stars are whirling around as if they were orbiting a really dense mass. That's where the black hole is. We can detect the motion of these stars with different ground-based telescopes like the Very Large Telescope and with space-based telescopes such as the Hubble Space Telescope.
When galaxies collide, it means their supermassive black holes at the center of each galaxy collide as well. Recently, astronomers have detected a triple collision of galaxies, each containing a supermassive black hole. For this discovery, astronomers needed to combine data from telescopes both on the ground and in space. Several observatories, like the Chandra X-ray Observatory and other NASA space telescopes, have witnessed this unusual event, which is located a billion light-years from Earth. First, the Sloan Digital Sky Survey Telescope in New Mexico imaged the system in optical light. Then, citizen scientists involved in the Galaxy Zoo project helped tag the system as a galactic collision. Shortly after, NASA's Wide Field Infrared Survey Explorer revealed glowing infrared light coming from the collision. To follow up on these clues, astronomers then turned to Chandra, which revealed X-ray sources at the bright centers of each galaxy, just where the supermassive black holes are expected to reside. And finally, NASA's Nuclear Spectroscopic Telescope Array spotted gas and dust around one of the black holes, typical for a merging black hole system. When researchers combined all this data, the final result revealed active, feeding supermassive black holes. While astronomers have observed pairs of black holes before, this is the first time they have witnessed a trio. Finding a triplet of supermassive black holes is very difficult because the gas and dust created by the galactic merger can hide the event from our view.
But this is all thanks to our powerful telescopes, which can see in different wavelengths rather than optical light. Eventually, the trio will merge into a larger one, producing gravitational waves or ripples in space-time, which can be detected here on Earth by radio telescopes. For the first time ever, an international research team has observed 3 supermassive black holes at the core of the galaxy NGC 6240. Every galaxy, including our own Milky Way, has at least one supermassive black hole that powers them. But scientists have now proved for the first time ever that a galaxy can have not one but 3 supermassive black holes. NGC 6240 is known as an irregular galaxy due to its unusual shape. The galaxy lies around 300 million light-years away from us, which is pretty close by cosmic standards, and due to its proximity, astronomers have been able to study it in all wavelengths of light. Previously, astronomers thought the collision of 2 smaller galaxies created NGC 6240, and therefore thought the galaxy contains 2 black holes in its core, until they found the third one. Each of them has a mass of more than 90 million suns. The researchers obtained the new observations of the galaxy using the European Southern Observatory's Very Large Telescope in Chile. These galactic ancestors moved towards each other at velocities of several hundred kilometers a second, and they are still in the process of merging. All 3 of the black holes lie in a region of space less than 3,000 light-years across. This discovery will help us understand the evolution of galaxies over time, especially the largest galaxies in the universe. Black holes are incredibly fascinating. I mean, they are invisible beasts lurking in space, sometimes ripping passing stars in half, scattering their remains. But how do they form? First of all, they are definitely not holes, so don't let the name fool you. Rather, they are a great amount of matter packed into a very small area. If we use some analogy, a black hole is basically like a star, 10 times more massive than the Sun, squeezed into a sphere roughly the diameter of New York City. Therefore, its gravity is enormously strong. However, different types of black holes form through different processes. Stellar mass black holes are born when very massive stars, tens of solar masses, can no longer produce energy in its core, so they explode in supernovae. These explosions are some of the most energetic phenomena in the universe. So after the outer layers of a dying stars are violently ejected into space, the remaining core collapses under its own weight to form a black hole. As for the formation mechanism of supermassive black holes, there is still a debate going on. However, it is generally agreed that a black hole in the center of a galaxy could become a supermassive by accreting matter and merging with other black holes. But the origin of the progenitor black hole is still unclear.
Astronomers have spotted strange flashes coming out of the Milky Way's central black hole, the Sagittarius A. Back in May, astronomers Tuan Do and his colleagues were observing Sagittarius A using the Keck telescope on the summit of Mauna Kea in Hawaii. They observed unusual blasts of radiation coming out of it. The flash of infrared radiation was more powerful than ever. In a period of just 2 hours, they witnessed the black hole become 75 times brighter. The researchers suggest the flashes could indicate that our central black hole has become more active or that it has started accreting more or different material. Once the black hole starts eating nearby objects like stars or dust clouds, the infalling material heats up at the even horizon, therefore lighting up the region. Even though the gravitational field there warps space to the point that light can't escape, telescopes can still pick up the radiation coming out of the event horizon. Astronomers speculate that the flash was thrown out when a star known as S2 moved close to the black hole in 2018, disturbing gases at the event horizon enough to cause the flashing event. Another reason might be a cloud of dust known as G2, which passed about 36 light hours from Sagittarius A in 2014. However, more observations might shed light on this mystery.
Black holes usually tend to destroy stars. But researchers have just witnessed a black hole that is actually helping to nurture and spark the birth of baby stars across multiple galaxies. Yep, the black hole is impacting stars in more than 1 million light-years from its origin. For this, astronomers used NASA's Chandra X-ray Observatory and some other telescopes. The supermassive black hole lies at the center of a galaxy 9.9 billion light-years away from us, and there are at least 7 galactic neighbors around there. Black holes devour everything caught within their gravitational pull. But they can also release highly energized jets of material that spew particles at the speed of light. Previously, scientists detected radio wave emission from a jet of high-energy particles stretched for 1 million light-years. Follow-up observations from Chandra revealed the black hole to be the source of the jet. Chandra can detect the X-rays created by hot gas that swirls around black holes. The Space Observatory also detected a diffuse cloud of X-ray emission surrounding one end of the radio jet. Scientists think this emission is most likely coming from a gigantic bubble of hot gas heated by particles in the jet when they interacted with the surrounding matter. So the researchers determined that the gigantic gas bubble expanded and actually moved across 4 of the neighboring galaxies. And that may have created a shockwave that compressed cool gas in the galaxies, causing stars to form. All 4 galaxies are about 400,000 light-years from the center of the bubble. The researchers believe star formation in these galaxies is 2 to 5 times higher than other similar galaxies. Months ago, astrophysicists at a Western university have found evidence that shows black holes don't necessarily need to emerge from a star remnant. This may explain the presence of extremely massive black holes at a very early stage in our universe. Shantanu Basu and Arpan Das from Western's Department of Physics and Astronomy have developed a new mathematical model explaining the observed distribution of supermassive black hole masses and luminosities. Researchers suggest that supermassive black holes actually form really quickly over a very short period of time, and then they suddenly stop growing. The new model calculates the mass function of supermassive black holes growing rapidly in a short space of time. This explanation contrasts with the current understanding of how stellar mass black holes form, and until now, theories suggested these black holes emerge when the center of a very massive star collapses in upon itself. So the new evidence suggests that black holes originate from direct collapses and not from stellar remnants. During the last decade, astronomers have observed many of these celestial objects at high redshifts. They dated back to within 800 million years after the Big Bang. The idea of these ancient black holes challenges the current understanding of how black holes form and then grow. Basu believes they can combine these results with future observations to infer the formation history of the extremely massive black holes that exist at very early times in our universe.
New research shows scientists might have been missing an entire class of black holes that they didn't know existed. In a study published recently in the journal Science, astronomers offer a new way to search for black holes. They suggest there's a class of black holes smaller than the smallest known black holes in the universe. Black holes are the corpses of what used to be massive stars that explode and ultimately collapse in on themselves. But not all stars turn into black holes. When some stars die and collapse, they form neutron stars, which are small and incredibly dense. The search for black holes and neutron stars helps researchers piece together how the universe works and how stars live and die. But if astronomers only focus on supermassive black holes and neutron stars, they are missing whole demographics of the population. The researchers began analyzing data from the Apache Point Observatory Galactic Evolution Experiment, which collected light from 100,000 stars in the Milky Way. Then they spotted something strange. A giant red star that seemed to be orbiting something. Shifts in the wavelengths of the star could show that the star was orbiting an unseen companion.
Based on their calculations, it had to be smaller than any observable black holes found in the Milky Way, but way bigger than most known neutron stars. After more calculations and additional data from the Tillinghast Reflector Echelle spectrograph and the Gaia satellite, they realized they had found a low-mass black hole likely about 3.3 times the mass of the Sun. Most galaxies have a supermassive black hole at their center. A few, though, contain not one, but two black holes. This is NGC 7674, the brightest and largest member of the Hickson 96 compact group of galaxies. The galaxy lies in the constellation of Pegasus, about 400 million light-years away from Earth. The center of this spiral galaxy boasts a pair of black holes orbiting around each other and separated by just over 1 light-year. The binary system appears to have a combined mass of about 400 million suns. Astronomers confirmed the existence of binary black holes by detecting gravitational waves emitted by them using the LIGO telescope. By analyzing observations of NGC 7674 made by the Very Long Baseline Array, scientists found two distinct compact sources of radio wave emission at the center of the galaxy. These monster black holes orbit their common center of mass about once every 100,000 years. The most likely scenario about how these black holes ended up spiraling in toward each other is the merger of two galaxies to form the current NGC 7674. The only other galaxy known to have two black holes at its heart is a giant galaxy called 0402+379, whose two giant black holes are separated by about 24 light-years. In 1973, Stephen Hawking predicted that black holes can eventually evaporate entirely, and for the first time, physicists have confirmed. Professor Hawking suggested black holes are not perfectly black, and they actually emit particles. According to Hawking, this radiation could, in the long run, suck sufficient energy far from black holes to cause them to vanish. Even though the hypothesis was once seen as impossible to prove, it is now broadly thought to be valid. The so-called Hawking radiation is extremely faint for our instruments to detect it in space. But scientists have seen this radiation in a black hole analog, utilizing sound waves and probably the strangest and coldest matter known to humans. Even though the vacuum of outer space is generally believed to be empty, quantum mechanics states that a vacuum is full of virtual particles that pop in and out of existence in matter-antimatter sets. However, near a black hole, the massive gravitational forces will pull the particles apart, therefore absorbing one into the black hole and shooting the other off into space. The escaping particle becomes known as Hawking radiation. The absorbed particle has negative energy, which reduces the black hole's energy and mass, So, if a black hole swallows enough of these particles, it will eventually evaporate. For the first time ever, astronomers say they have detected ripples in space coming from a black hole eating a neutron star. On Wednesday, the 14th of August 2019, both the Advanced Laser Interferometer Gravitational Wave Observatory in the US and the Virgo detector in Italy detected ripples in spacetime. They were coming from a cataclysmic event that happened about 900 million light-years away from Earth. Gravitational waves are created right before two massive objects collide. Astronomers analyzed the gravitational wave data to estimate the exact size of the two objects and then figure out what each one was. If both objects are between 1 and 3 solar masses, they are most likely neutron stars. If both are more than 5 solar masses, the event probably involved two black holes. But on Wednesday's detection, astronomers found one object was over 5 solar masses, while the other came in under 3. That strongly suggests this is a collision between a black hole and a neutron star. Black holes and neutron stars are the super dense remains of dead stars. However, scientists need some time before publishing the final results. Usually, when we think about black holes, we think about destruction. But a new research suggests the radiation coming from a black hole could in fact help cook life on some planets. Every star has a region around them where temperatures are just right for liquid water to exist on a planet. That region is called the Goldilocks zone. A new study suggests that even black holes have a similar region. The swirling disk of gas and dust around a supermassive black hole is called the active galactic nucleus. This disk forms when a black hole eats matter from its galaxy. As the matter swirls, it emits extreme amounts of radiation and light. Previously, scientists thought this radiation could strip the atmospheres of any nearby planets, therefore creating a dead zone around the black hole. Recently, researchers created some computer models of an active galactic nucleus to look at the swirling disk of gas and dust. Using these models, they detected galactic Goldilocks zones surrounding black holes. Simulations show that if a planet is positioned at the right distance from the black hole, its atmosphere would remain intact, while the black hole's radiation could break the atmosphere's molecules into life-supporting compounds. This radiation could even power photosynthesis, a process by which most plants utilize the sun's energy to create sugars. This would be particularly important for plants on rogue planets, which are free-floating planets with no parent star to provide a light source. For a black hole the size of Sagittarius A, the Goldilocks region would extend about 140 light-years from the center of the black hole. Contrary to previous estimations, scientists now think the damaging effects of black hole radiation would end at around 100 light-years away from a Sagittarius A-sized black hole. Astronomers using ESO's Very Large Telescope have discovered gas halos around some of the universe's earliest galaxies formed more than 12.5 billion years ago. Those reservoirs of cool gas provide food for the supermassive black holes located at the center of most galaxies. Black holes consume dust and gas from surrounding galaxies in order to grow. This explains how supermassive black holes, which likely formed due to the collapse of the first stars, were able to grow so large and so quickly in the early universe. Up until now, astronomers had not witnessed any evidence of enough black hole food to support the growth. Using the Very Large Telescope, the astronomers studied 31 quasars, which appear today as they would have been over 12.5 billion years ago when the universe would have been around 870 million years old. An infant in astronomical terms. 12 of those quasars were surrounded by huge halos of cool, dense hydrogen gas extending 100,000 light-years from the central supermassive black holes. However, they remained closely bound, offering a potential food source for these supermassive black holes. The astronomers said that with the current studies we are only just beginning to investigate how the first supermassive black holes were able to develop so rapidly. Astronomers from the University of California have found that powerful winds produced by supermassive black holes in the centers of dwarf galaxies slow down or even stop star formation, therefore impacting the growth of these galaxies. The winds they found were stronger than they had anticipated. That means black holes don't just impact the growth of larger galaxies, but also play a role in the development of dwarf galaxies. These types of galaxies contain anywhere from a few thousand to a few billion stars. The researchers used data from the Sloan Digital Sky Survey, which maps more than 35% of the sky, to identify 50 dwarf galaxies, 29 of which showed signs of containing black holes in their centers. 6 of these 29 galaxies showed evidence of high-velocity winds of ionized gas. Astronomers then used the Keck telescopes based in Hawaii to both detect and measure the properties of these winds, marking the first time this has been achieved. Larger galaxies often form when dwarf galaxies merge together. So by studying dwarf galaxies, we will be able to better understand the evolution of galaxies in general. The answer to what causes the winds is found in the material that's being fed into a black hole. When gas and dust falls into a black hole, it heats up due to friction and strong gravitational fields and releases radiative energy. This energy then pushes gas out of the galaxy's center and into intergalactic space. But when all the wind gets expelled from the center of the galaxy, gas becomes unavailable and star formation decreases.
The theory, which builds on ideas that have been mulled over for decades now, states that when something is sucked into a black hole, it's not lost to the universe forever as you might expect. Instead, Professor Stephen Hawking says that the information is stored not in the interior of the black hole, but on its boundary, the event horizon. What happens on the event horizon is rather complex, and even physicists struggle to describe it. One analogy, based on a theory devised by the American and Dutch physicists Leonard Susskind and Jarrard, is that as a body falls into a black hole, its information leaves behind a kind of two-dimensional holographic imprint on the event horizon, which is sort of bubble that contains a black hole through which everything must pass. Though you may be lost inside the black hole, the essence of you, the information about you, will stay smeared on the event horizon just outside. Hawking's theory is that the information can then escape again. In one of the previous discoveries, for which he's famous, he found that black holes aren't perfectly black. They give off energy, called Hawking radiation, which is created very near the event horizon by small energy fluctuations in space. So Hawking now theorizes that this outgoing energy can pick up the information blueprint sitting on the event horizon and carry it back into the universe. Though the information might have escaped the black hole, it's not exactly its former self. The information has now returned in a chaotic and useless form.
Many people have asked if the Sun will ever become a black hole. The answer is no. It is true that stellar black holes form by the gravitational collapse of a star, a massive star. But our Sun would need to be about 20 times more massive in order to go supernova at the end of its lifetime and then collapse back into a black hole. However, there are also stars that are big enough to go supernova but still too small to become black holes. When these types of stars go supernova, they collapse into super dense structures called neutron stars. But what about the Sun? In about 5 billion years from now, the Sun will start to run out of fuel and begin to collapse. The Sun's temperature will increase, and its outer layers will expand so far out into space that they will engulf Earth. This time of our star is called the red giant phase, and will last about 1 billion years before the Sun eventually collapses into a white dwarf. A white dwarf is a small, very dense, burned-out core of a star, typically the size of a planet. The outer layers of the Sun's atmosphere, which have been blown away, will create a planetary nebula that will glow for the next 20,000 to 50,000 years, expanding outward and fading slowly with time.
Quasars are the brightest objects in the universe. They are powered by supermassive black holes and emit exceptionally large amounts of radiation. Ton 618 is a very distant and extremely luminous quasar. It's an accretion disk of intensely hot gas swirling around the most massive black hole known to mankind. It might be about 66 billion times the mass of the Sun. For reference, Sagittarius A, supermassive black hole, found at the center of our galaxy, is a shrimp measuring at only 4 million times the Sun's mass. Astronomers first noted Ton 618 in a 1957 survey of faint blue stars. The light originating from this object is estimated to be 10.4 billion years old. The surrounding galaxy is not visible from Earth because the quasar itself outshines it. The enormous quasar shines as much as 140 trillion suns, making it one of the brightest objects in the universe. It lies near the North Galactic Pole in the constellation Canis Venerici.
Using Hubble Space Telescope, astronomers have caught something unusual happening at the heart of the spiral galaxy NGC 3147. The galaxy lies about 130 million light-years away from us, and like most other galaxies, it contains a supermassive black hole at the center. But what scientists didn't expect was the thin disk of material furiously whirling around the black hole, which has a mass of around 250 million times that of the Sun. Some say the disk shouldn't be there at all. That's because even though the galaxy is active, it's a low luminosity one. Black holes in galaxies such as NGC 3147 are usually pretty quiet and starving because there isn't enough material in the galaxy to feed them regularly. However, this mysterious disk offers a unique opportunity to test Albert Einstein's theories of relativity. Hubble showed that the gas is embedded deep within the black hole's gravitational field, which has altered light in a way that astronomers can actually see what's happening close to the black hole. The telescope has also measured the disk of material, and astronomers determined that it's rotating around the black hole at more than 10% the speed of light. Because the gas disk is so deeply embedded in the black hole, the light can't escape, so it looks stretched. Using Hubble's imaging spectrograph instrument, astronomers were able to take the light and separate it into wavelengths, which helped them indicate temperature, speed, and other information. Now, astronomers want to search for other disks surrounding black holes in similar low luminosity galaxies to NGC 3147.